Question overview. A long tube open at one end and sealed at the other end is partially filled with water. A vibrating tuning fork with a frequency of 512 Hz is placed on the top of the opening end. This vibration produces the first loud sound. The water level will be controlled by this valve. Then some of this water runs out of the tube by opening this valve. Then a second loud sound is produced. The figure 6.1 shows the waveform with this water height, and now is asking what will be the waveform for this new water level. Before drawing the waveform in this tube, I want to review stationary waves. This is a wavelength of a traveling wave. When this traveling wave finds an obstacle, will reflect back. This wave is representing the reflected wave. So the traveling wave comes, find an obstacle, and reflect backwards for a single wavelength. This is the length of a complete wavelength. Now, this will be half of a wavelength, and this is 1/4 of the wavelength. So if this is a complete wavelength, this section will be half of a wavelength, and this section will be 1/4 of the wavelength. Because this wave is traveling and finds this obstacle and reflects back with the same wavelength, the same amplitude and frequency, this is called a standing wave. So a standing wave is a combination of the wave and its reflection. This is a standing wave. Now I'm going to isolate just this quarter of this standing wave. So this is just 1/4. Now imagine this is my wave and this is my standing wave. So they are inverse of each other. So sometimes when the one is up, the other one is down. Sometimes they are together the same line and they change direction. The interaction between a wave and its own reflection produces a section of maximum displacement known as antinode and no displacement known as node. In this example, with just one single wavelength, we can identify 2 antinodes and 1, 2, 3 nodes. For this quarter of a wavelength, we have here 1 node and 1 antinode. As we observe those 2 waves independently, so this will be the amplitude of the wave, the original one, and this one will be the amplitude of its reflection. So here we have from the resting line or equilibrium line to the maximum vertical displacement, and that is the definition of amplitude. So we have here A1 for the original one, and let's call this one the inverse, the inverted one, the reflected one, A2. If this stationary wave with one wavelength will be a sound wave, the amplitude of a sound wave is equal to the volume. So here in this case, you have the amplitude of the original wave, and we have the amplitude of its reflection. In this antinode area of this quarter of this complete wavelength, the volume is equal to the sum of the amplitude of the original wave plus the amplitude of its reflection. So in this area of antinode, the sound is louder. When this fork is set into vibration, so the waves produced by the fork will be in something like this, and so on. So which means that these will be the crests, and between we have the troughs. So it's like it's going this way. So this is a open pipe and close at the end. It's just air here. If I set this fork into vibration, so the sound is going to travel inside this pipe. So let's pretend the sound produced by this fork is going to travel inside this open pipe with this direction. As the sound wave reaches the obstacle, because this pipe is sealed, is going to travel back. This is its reflection, so it's going to travel back in opposite direction. Then we can identify here the antinode, another antinode, and another antinode. So a listener should hear at the open section a very loud sound. Another sound that is loud, you'll be right here and you'll be right here. However, the listener will not be able to identify because this is where the listener is located. Now, one important information: if a node of this stationary wave produced inside this pipe, you'll be right here instead of the antinode, the listener will not be able to hear any sound. Now, let's turn this pipe upwards. It will look like this. Now, first example, our tube here was just filled with air. So with the torque vibration, we will produce a sound because the antinode is right on the opening of this tube, whereas listener is trying to identify a loud sound. Now, instead of air, we have here water is partially filled, and now the water level will be the obstacle for the sound wave produced by this vibrating tuning fork. If the listener is able to identify a loud sound, for sure in this opening we have a antinode produced by the wave and its reflection. So this is the node right when hit the water. Remember, the wave will stop right here and will reflect back because the water level now is an obstacle. Now let's imagine this scenario. So a listener is holding a tuning fork that is vibrating on the top of this opening, and there is a water escape right here. So the water is flowing at constant rate. And what is going on is now the sound has more space to create a wave, and is going to find this obstacle with the water level as the water is going down, and then it's going to reflect back. So the listener is going to hear a loud sound twice. And first that will be your first loud sound, that will be your second loudest sound, because it's going to hit the area of antinode. Before moving forward, I would like to address a common misunderstanding about adding the vertical displacement of a standard wave with the principle of superposition. The amplitude of the ongoing wave, A1, and the reflected wave, A2, meet on the antinode where the maximum displacement occurs. This antinode is an area of constructive interference because we are adding two amplitudes of one wave and its reflection. Now we have here two separate waves, A and B. They are independent of each other. B is not a reflection of A, but they are traveling the same median at the same time. And when they overlap, let's say they do just like this. When they overlap, the resultant displacement is the sum of individual displacement of each wave. So in this case, because both waves, they are opposite of each other, we are going to have a destructive interference right in the section. So there is no wave. There will be a complete flat line. Comparing side by side a stationary wave and two traveling waves in terms of interference, we can notice here that for a stationary wave, we have a wave A, and wave B is the reflection of the original wave. So when they interact with each other, so they're going to create an area of constructive interference, which means that the vertical displacement will be maximum right here, right on the crest and the resting line, and this will be the maximum interference, which is the maximum constructive interference. In the case of two traveling waves, they are independent of each other, and in this case, same example, one wave A and wave B is the inverse of A. So when we add those vertical displacements, so we are going to have as a result a flat line, which is the result of the interference of those two waves traveling the same median, and these will be complete destructive interference. So back to our problem, we need to sketch the standing wave inside this tube. So we know that this first loud sound will be right here, right? So we are going to use this to guide us to draw the second part. I'm going to flip this pipe to make it easier to draw. I'm going to mark this node right here because that's where we have our next water level. And I know this is another node that was defined by the prior water level. So I'm looking my second loud sound. And this must happen when I have my second antinode. Remember from our prior diagram, when I was explaining how a stand wave is traveling inside a pipe. So between two nodes, we have one antinode. The same idea we have in this picture. So we have a node, a node, so we must have an antinode right here in the middle. So now I'm going to complete my traveling wave produced by this vibrating tuning fork. So the wave go this way and up and go here and then come back. This is the reflected one. So that will be our sketch. Then you label here the first loud sound, and right here will be our second loud sound. And this is the node, and this is the node. So questions A, I ask you to sketch the form of a stationary wave set up in the tube, and that's how it should look like. And the II, it says mark with the letter uppercase N the positions of any nodes of the stationary wave. So here we have a node and we have our second one. Moving forward, question B. The frequency of the fork is 512 Hertz, and the difference in the height of the water level for the two positions where a loud sound is heard is 32.4 centimeters, as indicated in this picture right here, between the first and the second water level. Calculate the speed of sound in the tube. The only formula that involves frequency, wavelength, and speed of a wave is this formula. Speed of a wave is the wavelength times frequency. Now let's remember the sections of a wave. So this is a complete wavelength, and now we have half, and this is a quarter. So let's try to identify parts of a wave in the standing wave in the tube. So in this picture, between two nodes, I have half of a wavelength. Likewise, half of a wavelength is right here and is equal to 32.4 centimeters. So that's the half of a wavelength. So from our diagram, half of a wavelength between two nodes is equal to 32.4 centimeters. According to this picture, between two nodes, we have half of a wavelength, which is equal to this. So the wavelength is 2 times 32.4 centimeters. In terms of meter is 0.648. Why am I converting? Is because the speed is given meters. Making the substitution, so the wavelength is 0.648 meters times the frequency of the fork. So the velocity of the sound wave is 331.77 meters per second, or rounding to 332 meters per second. Question C. The length of the column of the air in the tube in figure 6.1 is 15.7 centimeters. So the air column in this tube is 15.7 centimeters. Now the question is asking to suggest where the antinode of the stationary wave produced in the tube is likely to be found. From question B, we determined that the wavelength of this stand wave is 64.8 centimeters. However, the air column here is showing just a quarter of a wavelength. So that means that their column shows just 1/4 of the wavelength. So 1/4 of this 64.8 centimeters is 16.2 centimeters. So the problem states that the air column has a length of 15.7 centimeters. However, the quarter of the wavelength is a little bit higher than that, which is 16.2 centimeters. So to answer this question, we can say that the antinode would be 16.2 centimeters above the water surface. So this problem involved standing waves, the understanding of how to draw a standing wave in a pipe for sound wave, using the wave equation to find the speed of this wave, and the understanding of the portions of a standing wave, in this case a quarter, and compare with the water level.